All right, a little idea of a math teacher's joke. If you really think you only live once is a nice comment to put on a math quiz. You can see how this teacher reacted, pointing out a little math study might definitely pay off in the end. We're doing some homework problems with fundamental theorem and mixing practice together here with derivatives, indefinite integrals without limits, and definite integrals. So you want to make sure you have all three strategies. So our derivative here is a power rule. So we've been doing this for quite a while, so matters not whether you write this with a denominator or a negative exponent. But now we have to reverse our power rule to do the integral of x to the negative 2. So there we want to raise the exponent by 1 and then divide by it. And you can check to see if you did the derivative. That's always your method of checking your integration, is if you do the derivative, will you get back to the integrand? And then we're doing the same integrand, but this time we have a definite integral. So remember our notation for our fundamental theorem. We want to take the antiderivative at the upper limit minus the antiderivative at the lower limit. So we've just done the antiderivative, so we could write it this way, evaluated from 1 to 5, or we could write it as the opposite of 1 over x, evaluated from 1 to 5. And these bars here you could see this way. You could put it in square brackets. Those all mean the same notation. So we don't need the constant, remember, when we evaluate, because there would be a constant on both parts here. So you would have the constant minus the constant. That's an easy way to explain. So now we just need to do our substitutions. So our capital F of b would be negative 1/5, and then we subtract the value at the lower limit. So we have negative 1/5 plus 1, so we will be at positive 4/5. So remember that when you evaluate an indefinite integral, we get a function. And when we evaluate a definite integral, we get a numeric value. All right, so let's try again here. We've got a power rule, so 5x to the 4th. So now we want to integrate x to the 5th, so we reverse the power rule, and we divide by the new exponent. And again, should make perfectly good sense that if you do the derivative, you can check to see if you get back to the integrand. And then we've got the same integrand, but this time we're doing a definite integral. So we will have 1/6 x to the 6th evaluated from negative 1 to 2. And you could factor the 1/6 out of both terms and take care of it later. You could do this whichever way you want. Then we would just have the x to the 6th. So 2 to the 6th power is 64, and negative 1 to the 6th power is positive 1. So we have 1/6 of 63, so 63 over 6, or of course you could divide that by 3, I suppose, and have 21 halves. The derivative of cosine is negative sine of x, or opposite of sine of x. The integral of cosine, cosine is the derivative of sine, and we add a constant. And for evaluating our definite integral, oops, let me try getting back here to the right size. Sorry, I had reduced and scrolled there. Let's try doing the integral of cosine is sine, evaluated from 0 to pi over 3. So we'll have the sine of pi over 3, and you don't have to show this step, But let's just make it very clear what we're doing. Sine of pi over 3 minus sine of 0. And the sine of pi over 3 is the long leg of a 30, 60, 90. And the sine of 0 is 0. So square root of 3 over 2. And only show as much work as you need to there. In number 4, the derivative of secant squared requires a power rule first, and then a chain rule on the secant. The derivative of secant is secant tangent. So we could rewrite this as secant squared, but tangent only to the first power. And the integral of secant squared is a very different matter. Secant squared is the derivative of what? That is the derivative of tangent of x. And we add a constant. And then when we evaluate it as a definite integral, we're going to evaluate tangent of x from pi over 4 to pi over 3. So we want the tangent of pi over 3 minus the tangent of pi over 4. Tangent of pi over 3 is long leg over short leg, so it'd be square root of 3. And pi over 4 is an isosceles right triangle, so the legs are congruent. So the tangent of pi over 4 would be 1. And we could use our calculator and round that to 3 decimal places, but an exact answer is always acceptable. In number 5, derivative of e to the x is e to the x. So the integral is e to the x plus c. And then we evaluate e to the x from 0 to 3. So we would have e to the third minus e to the 0. And of course, e to the 0 is 1. So again, you could change that to decimal form and round it off, but why not leave the exact answer? To do the derivative of 1 over x, think of it as a exponent, x to the negative 1. So we'll reduce the exponent. So negative 1 over x squared, either one of these two forms, of course, would be a fine answer. As opposed to the integral, 1 over x is the integral of the natural log of x, assuming that x is not equal to 0. And we're evaluating, and notice here in our definite integral that's taken care of our limits, we're going from 1 to e. So we know that 0 is not in that interval. So we don't have to worry about an absolute value since we're doing a positive range. So the natural log evaluated from 1 to e. So the natural log of e minus the natural log of 1. The natural log of e is 1, and the natural log of 1 is 0. So we get the value 1. So we simply need to make sure that you keep doing enough practice. If this homework assignment wasn't quite long enough, you can go to the Moodle site and find more practice, but you want to make sure that you have your derivative rules very quick and ready to access so that now you can use them when you are doing anti-differentiation.